Welcome again to the second video in a series that's going to enable you to evaluate yourself, to do some self-evaluation. And the topic of this one has to do with, in your mind, can you create in your mind what the plot y versus x of specific functions look like? We're going to go through some simple examples with increasing difficulty. So let's get started. So what we want to do is want you to check out how well you're prepared to visualize y equals some function of x. So in other words, like a formula that's based on x. And this is going to be extraordinarily important as you begin your mechanical engineering classes. We want you to perform well in classes, and the ability to quickly sketch by hand, doesn't have to be computer, ability to sketch by hand y equals f of x is going to be an important skill for you to perform well in class. What does perform well mean? Of course, it means to get a good grade in your class. On the short term, on the longer term, you're preparing yourself to be a practicing engineer. And we want both of those good things for you. So let's work through some examples on visualizing and then plotting y equals f of x. So in the ME department, you need to be able to quickly sketch frequently utilized functions, y equals f of x, with your pencil and paper, okay? Your sketch does not need to be a work of art. It's got to be good enough for other people to understand what you're drawing, but it does not have to be some perfect work of art. So a linear relationship, it is my hope that you're nodding your head and say, man, I've got this one nailed. Y equals mx plus b. I think I worked with these all the way back in elementary school. And so this familiar hand-drawn sketch should look pretty familiar to you. You should have a lot of practice. Y-axis, x-axis. Here's the intercept, B, okay? A linear line, a slope, okay? Now, just sort of for illustration purposes, I've plotted y equals mx plus b in Excel. But look, the expectation for you is you need to be able to just do this with pencil and paper. Hand-drawn sketch is going to work. And in mechanical engineering classes, typically we do a little more than just drawing a straight line, y equals mx plus b. In our engineering problems, typically we start at some point 1, and we've got some objective to get to point 2. And so that's why I'm sort of illustrating points 1 and 2 on my hand-drawn sketch. In the Excel, I've got a slope of 3.2 and an intercept of 2.5. So it's my hope that you're in pretty good shape on this y equals mx plus b. And the visualization of what that looks like. M is just some number, and b is just some number. Let's move to a little more level of sophistication. You'll be faced with another type of function, y equals f of x. Ax squared plus b, where a is some number and b is some number, and x is the variable. How would you plot that? You would recognize this as a parabola, right? I hope. At least had this maybe in junior high school up into high school, plotting a parabola of the form y equals ax squared plus b. Should be able to do this by hand. And of course, again, just for illustrative purposes, it's an easy matter to create that plot in Excel. For this one, I've got A, the intercept is, B, the intercept is 2.5, okay? And A, the higher the value for A, the more steep this parabola gets quicker, right? So high values of A, you're going to start seeing the parabola go up quickly. Low values of A, it's going to be going up in a lazy manner. But hopefully you say, okay, I think I'm good on this one. Y equals ax squared plus b. It's a parabola. Got it. The next one, I kind of gave away the name of this, but let's go back and think about high school. I was not introduced to this function, y equals a divided by x. I was not introduced to this till I was in high school. For you, maybe earlier, but in me, high school, y equals a over x, where a is some constant number. Well, we studied and studied and studied on this, and we learned that this is a special type of mathematical function called an hyperbola. This is a hyperbolic relationship, hyperbola. Okay, and so when you study on the numbers, when x is a small number, y is going to be a huge number. Okay, as x goes to 0, y gets huge. Okay, as x gets big, y becomes little. And so in high school, we got more familiar with this being a hyperbolic function. I do have to tell you that in mechanical engineering, we're going to deal with this function a lot. Okay. And the other part is I've shown in my dot one, we're going to typically do more than just draw in the hyperbolic line. We're going to start at some point on our x versus y graph at 1, and we're going to head towards a new point 2 on the hyperbola. Okay, and so again, here in Excel, I've just sort of plotted this for a value of 3.2. Okay, and so of course, here's what the beautiful Excel plot looks like. You don't need to be able to create this in Excel or MATLAB or anything else, but by golly, you do need to be able to draw this by hand, a hyperbola, y equals a over x. Now, a very important point I want to make, and I hope that you stick with me on this. In high school, we learned y equals f of x, and the function of x equals a over x, where a is some number. Got it? Okay. So you got familiar with that. This list of formulas are all identical. These are equivalent. They're identical to one another. Simply multiply both sides by x to get xy equals a. Next line down, flip y and x, yx equals a. Now I've circled that. This is the most usually observed form of the hyperbola that you're going to encounter in your thermodynamics class, yx equals a. And then I'm working up to something else. Recognize that you could also write this y times x to the 1 power equals a. So you see how these last two are identical. X is also x to the 1. Okay. But anyway, get comfortable with the way we can write different forms of the same function, the hyperbola. Now we're moving on to a function that is even more complex than the hyperbola. And I will have to admit that I did not cover this in high school very much. Okay. It wasn't until college that I got to this, what I'm calling a power relationship, y equals a divided by x to the k. And I'm giving you a little foreshadowing of could you plot this by hand? Well, what I've done is I've drawn in a hyperbola, y times x equals, well, a, or a constant, c, okay? And then I've drawn in a power function that's a little steeper for low values of x, little steeper. So I'm going to do this in Excel. So in Excel, I've plotted this out with a with a value of 3.2. And so notice here what I've done here. I just showed on the previous slide, y equals a divided by x to the k. Do you see that that is equivalent to a x to the minus k? So be very important to recognize this. A divided by x to the k exactly equals a x to the minus k, where a is some positive number. K is some positive number. And typically, let's just pick k of 1.3, not 1.0, let's say 1.3. And so when k is 1.3, for low values of x, it's going to be steeper than the hyperbola y equals x, xy equals constant. Okay. So anyway, in yellow, the curve is steeper than the hyperbola for low x, and it's flatter than the hyperbola for high values of x. Okay. Don't be nervous, but we are going to be using this function a lot. Now, I've refreshed this slide about ways to express a power relationship in equivalent manners. So y equals a divided by x to the k. That's sort of our starter point. Recognize we can also express it y equals a x to the minus k, where k is some real number, okay? And let's rearrange. Let's see. Let us multiply both sides by x to the k. X to the k times y equals a. That's an equivalent statement, okay? Or let's flip y and x to the k. This last entry, these are all equivalent. Y x to the k equals a. And I want you to see that this is the most usually observed form that we encounter in thermodynamics. Y x to the k equals a. So when you start seeing this, you got to back up a little bit and say, oh yeah, that's going to be a power function, and that's really y equals a divided by x to the k. Okay. Mental exercise here. So we're going to pause on these power functions. In general, if we've got y x to the k that we observe a lot in thermodynamics class, y x to the k equals a, some number. What is the shape of the curve when k is 0? You use your head to think of that without drawing it. When k is 1, what does y versus x look like in your head? When k is 1.2, what does y versus x look like? 1.3, 1.4. So think in your mind. I'm gonna give you a minute. What do the curves look like before the big reveal? Can you think in your mind? Could you draw y versus x for all these situations? Okay, when k is 0, y times x to the 0 equals a. What's x to the 0? That's 1. So y equals a. It's a horizontal line. Okay. Think about that a little bit. Okay. When k is 1, yx equals a. That's a hyperbola. Just covered that. When k is 1.2, well, that's going to be a power curve. It's going to be a little steeper for low values of x. It'll be steeper than a hyperbola. When it's 1.3, it's even going to be steeper than k is 1.2. And when it's 1.4, when k is 1.4, it's going to be even steeper than k is 1.3. So there you go. I hope you, oh, and notice here, my little arrow here. Notice the similarity between hyperbola, x to the minus 1, and the power curve, x to the minus k. So that's it. Notice the similarity there. Now let's get you prepared for thermodynamics even more. So I think it's great. You've been through high school and you've been through college math. Okay, you've been through both high school and college math, and you've dealt with mathematics problems that had variables y and x. Now we're moving into the mechanical engineering world, where the variable p, we're not even going to mention what that p is, but p is going to take on y. P is going to be like y. And the variable little v is going to be like x. So you're going to be plotting, instead of y versus x hand drawn, you're going to be plotting p versus v. And you're going to be doing all kind of other different types of graphs. But early on in thermo, you're going to be drawing graphs where p is like the y-axis and v is like the x-axis. So you're moving from high school and college math, and you're moving ahead into mechanical engineering. You're performing well because you're well-grounded in math. You're performing well, getting good grades in your classes, and you're going to be then performing well to train yourself how to become a practicing engineer. Okay, so this is kind of important. This is kind of an important slide. It looks easy, low word count, but kind of important. Let's do the same example of visualizing in your mind what would the shape of y versus x, or P versus V look like for P equals constant? P is constant. That's a horizontal line. P, kind of like Y, constant. Y is constant, horizontal line. How about little v? If v is constant, what's that shape going to look like? That'll be a vertical line. That's like x is constant. Okay. How about PV is equal to constant? That's a hyperbola. We just covered that. And how about PV to the K is constant? Well, that's going to be like a power curve. And when K is some real number greater than 1, it's going to be a little steeper than a hyperbola for low values of X or V, okay, and flatter for high values of X or V. Okay, so again, use your head. You will get better in this the more you work with it, okay? And so does that make sense to you? Think in your mind, be very honest with yourself. Does this stuff make sense? Y equals mx plus b makes total sense. Parabola, yeah, pretty familiar. Hyperbola, maybe a little more complex. Power curve, definitely more complex. So all these examples were fairly easy with increasing difficulty, but you're going to be getting better and better and better with this. We're visualizing the shape of the curve and drawing it down with pencil and paper. Now, let's be real honest with yourself. Okay. The first two you feel pretty good about. Okay. Are you feeling a little uncomfortable with the last two? A little uncomfortable. Well, maybe you could do a little self-review. Go to the internet, go to that Khan Academy deal maybe, and refresh a little bit before you get into your classwork. Okay. If the last two examples, if hyperbola and power curve were totally Greek to you, said, I've never seen this in my life. I don't understand it. I don't understand what that guy was doing with those hand-drawn curves. I am lost with that. I want to encourage you to go see your undergraduate advisor, because help is available at Virginia Tech. Help is available if you're totally lost for those two last examples. I think your undergraduate advisor can get you hooked up with the right people in the right departments to get you up to speed in that area. But I do want to give you a heads up, and that is that when you begin your mechanical engineering classes, our instructors and professors teaching these classes, we run the classes at such a rapid pace, sometimes a breakneck pace, that those instructors and professors will not be able to take the time in class or outside the class to review fundamentals of a hyperbola, fundamentals of a power curve. We'll be able to touch on it, but if you're totally lost with those, probably not going to be able to get the help you need from your mechanical engineering professor. We want you to excel. We want you to do well. We want you to get a good grade. If you're lost with these fundamentals, your action plan is see your undergraduate advisor, set up an action plan for getting familiar with these quickly. Okay. I hope that helps. And so the purpose of this video was for you to be thinking in your mind, can I look at the form of a function? Okay, can I identify it in my mind? And then can I hand draw a sketch that looks like that function? Okay, that's the idea. And anyway, I hope this self-review has helped you and encourage you to be thinking about that as you prepare to take your mechanical engineering classes. Wish you all the best.